Let's continue our derivations of trigonometric identities. Again, we're going to be using complex numbers in this video. Let's get started by recapping what we derived in the previous video. So in the previous video, we managed to get these two relationships. So the top one involving the cosine was actually the real component of that complex exponential. And this guy over here was the imaginary component. So we identified the real component with the real component and the imaginary component with the imaginary component. And that's how we managed to derive both of these guys over here. We're going to do a similar thing in this video. So in the previous video, what we were looking at is the sum of theta and phi. Theta and phi could be different angles, but they also could be the same angle. So let's examine the case where theta is equal to phi. What's going to happen to these two expressions if theta is equal to phi? Let's have a look at the top one. What's going to happen over here if we set theta equal to phi? Well, phi is going to turn to theta over here, and over here we're going to have a theta. So what we're going to have is cosine theta times cosine theta, sine theta times sine theta. So this is actually going to be, I'll write this out in full, we're going to have cosine of 2 theta, right? Because if we're adding the same thing, then we're going to get a factor of 2 inside. So cosine of 2 theta is equal to cosine squared of theta minus sine squared of theta. So where does this come from? Well, it comes from this expression. So this is actually just a special case of this more general expression. So this is a more general relationship that takes the sum of any two angles that don't necessarily have to be equal. But this guy is the special case where theta is equal to phi. So that is for cosine of 2 theta. And you can imagine this is a very useful thing to deal with, because this over here can be a lot more convenient to work with than this, because here you have a factor of 2 in front of the angle, and here you're just dealing with the angle by itself. Now let's have a look at the bottom one. So the bottom one, what's going to happen to it? Well, theta and phi are going to be equal to each other. So we're going to have cos theta sine theta, and over here we're going to have cos theta sine theta. So these guys are actually going to be the same term. So we're just going to have two copies of the same term. It's this mixed term that has cosine and sine multiplied together. So if we have sine of 2 times theta, that's going to be equal to 2 times cosine theta times sine theta. So we'll have cosine theta times sine theta. And you could actually change the order of these guys around. You could have sine theta, cos theta. That's because multiplication is commutative. So the order over here also doesn't matter. I've just consistently put cosine to be first over here, so we can keep track that theta actually gets swapped with phi in this expression. But over here, it doesn't matter. You can have cos theta or sine theta first, because there's only one angle that we're dealing with. So these guys are what happens if you take double the angle and you input that into the cosine and sine functions. So these guys are very useful, and they're just special cases of this more general form. Now, if you remember in the previous video, which you can find in the quantum mechanics playlist, there's a link in the description below. You can also click up here. Make sure you watch that previous video, because we actually used those complex exponentials. We had something that had e to the I theta and e to the I phi. So what we're going to do is we're going to do a similar thing, but we're just going to do one angle. We're going to see what happens if you add an angle to itself. So if you add an angle to itself, that's the same as multiplying this exponential, e to the I theta, by itself. We're just going to have another copy of that. We're going to have e to the I theta. So we have this guy times this guy. And that's exactly the same as e to the I theta squared. So it's like squaring this exponential. And this is also the same as e to the I times 2 theta. So I'll put 2 theta over here. And if you have 2 theta, we can expand this out in terms of cosines and sines, and that's going to give us cosine of 2 theta. I'm going to put brackets over here because we have more than one thing in the argument. So over here, where we have just one single angle, it's a bit redundant to put brackets because it's a bit unnecessary. You can see that the theta is definitely being acted on by the cosine. There's nothing else that could be acting on the theta. But over here, because we have 2 theta, it's more appropriate to put brackets. And the more complicated your expression is, the more useful it is to have brackets. For simple expressions, it's not useful to have brackets. So this is the real component, and now let's write the imaginary component. The imaginary component is I times sine of 2 theta. So we have 2 theta in there. So this is very similar to what we did in the previous video. In the previous video, we had theta plus phi up here, and then we had theta plus phi in here and in here. So what we're going to do now is we're going to do some algebraic manipulation, and we're going to have a real component and an imaginary component, and we're going to match them up again. And when we match them up, we're actually going to get these expressions. We're going to get the same expressions. So let's do that. We know that this guy is equivalent to just squaring. It's the same as going cos of theta, because that's what this exponential is. It's the same as cos theta I sine theta all squared. Right? That's exactly what this thing is. And we know this is actually the same as just multiplying that exponential by itself. So I'll write that out in full. So we have cosine of theta plus I sine theta. And we're going to have another copy of that. I'll write it over here. This is just so we can keep track of which terms are where. So we have cosine of theta plus I sine of theta. So we have 2 copies of that, right? We're squaring it. And I've written it out in full so we can match up all the terms. I'm going to write that below, and we're going to get an expression that has a real component and an imaginary component. So that is equal to, what's our real component going to be? So our real component is going to have no i's in it. And the imaginary component is going to have a single I multiplying every term in there. So how are we going to eliminate the i's? Well, this term and this term, they don't have any i's. So that's going to be real. This term multiplied by this term, that's going to have an I times an I, which is I squared. And I squared is minus 1. So I squared is equal to minus 1. So we can get rid of that I by multiplying it by another I. So what's our real component going to be? Well, the real component is going to be cosine squared of theta. That's what we get from the first terms being multiplied. And the last terms being multiplied together, it's I sine theta times I sine theta. The I squared is going to become minus 1, and the sine times sine is going to be sine squared theta. Now this should look familiar. This is what we have up in the top right corner. This guy is exactly the same as this guy. So now let's have a look at the imaginary component. The imaginary component is I multiplied by, what is the imaginary component? Well, it's going to be the mixed terms. We're going to have sine theta cos theta from this term over here, and we're also going to have cos theta times sine theta. So these are actually the exact same term. This and this are exactly the same. So we're going to have 2 copies of them. And if we have 2 copies, we're going to write a factor of 2, and then we'll have cosine theta and sine theta. So those are the 2 copies from these mixed terms. So that's these outer terms and these inner terms. And this is the imaginary component. It's the term that gets multiplied by I, right? Because both of these guys introduce 1 copy of I. We have 1 I over here, and we have 1 I over here. And we can factor that out, and that's going to give us this. So this you can identify with the imaginary component. Sine of 2 theta is 2 cos theta sine theta. And that's what we have over here. That's the special case of this thing that we derived in the previous video. And the real component, you can identify this expression, cos squared theta minus sine squared theta. That is the same as cos of 2 theta. And that's what we have written up here. So we've derived these 2 trigonometric identities using 2 different techniques. We've done it using complex numbers. So we've started with e to the I theta, and we've done some algebraic manipulation, and we've actually assigned these real components to each other and these imaginary components to each other. That's the same logic as the previous video. And the alternative derivation that we actually used at the beginning of the video was using these other trigonometric identities, which are more general, and then we've simplified them by imposing the condition that the angles have to be equal to each other. So theta has to equal phi. So that is what this video is actually about. It's the case where theta is equal to phi. And that is what we've done when we've gone from here to here. So we've just set those 2 angles equal to each other. So the reasoning, the fundamental reasoning is using these complex exponentials. There's something that's of the form e to the I theta, and then writing that in terms of cosines and sines. So all of these guys are going to have a real component and an imaginary component. So complex numbers are where trigonometry really starts to make sense. A lot of the things in trigonometry you can derive from complex numbers. And we're going to continue doing derivations using complex numbers, and we're going to find some very useful trigonometric functions. and some very useful trigonometric identities that are going to help us simplify complicated expressions. If you want to find more videos like this one, make sure to click over here.